The valence bond theory cannot correctly predict the magnetic behavior of a coordination complex. See the hexamine cobalt 3 complex ion. CO3 plus ion has its electronic configuration as follows. The 6 amine ligands are expected to bond with these empty orbitals in what is called sp3d2 hybridization. In that case, the magnetic behavior of the complex is expected to be paramagnetic due to presence of these unpaired electrons. This is not true. The complex is found to be diamagnetic with no unpaired electrons. Actually, in this case, the inner d orbitals take part in d2sp3 hybridization like this. The valence bond theory also cannot predict the shape of a coordination complex correctly. See the tetracyanonickelate 2 complex ion. Ni2 plus ion has its electronic configuration as follows. The 4 cyano-ligands are expected to bond with these empty orbitals in sp3 hybridization, and the shape would be tetrahedral in that case. This is not true. The complex is found to be square planar in shape. Actually, the inner d orbital is involved in what is called dsp2 hybridization. The failure of the valence bond theory to explain the correct coordination complex chemistry led to the discovery of the crystal field theory developed by Hans Bethe and John Hasbrouck van Vleck in 1930s. The crystal field theory assumes number 1, metal ligand bonds are ionic, number 2, ligands are thought of as point charges for anions or dipoles having negative ends for neutral ligands. We will talk of the d block transition metal elements of the periodic table, which mainly form coordination complexes due to presence of too many empty orbitals. Now, if the principal quantum number is n, the outermost electrons lie in the n-1 d orbitals. These d orbitals are degenerate. When a spherically symmetrical field of negative charges approach the metal ion, the d orbitals face electrostatic repulsive force and get energized. The degeneracy of the d orbitals is still maintained. Ligands approach the metal ion from specific directions. The d orbitals are oriented in different directions. Some d orbitals are directed towards the ligands, get energized, while other d orbitals directed away from the ligands get stabilized, that is, their energy comes down. The degeneracy of the d orbitals is lost, which is called crystal field splitting. We shall study the crystal field splitting under different geometry of coordination complexes. Octahedral geometry. These are the d orbitals. This is the dxy orbital. This is the dxz orbital. This is the dyz orbital. This is the dx square minus y square orbital. And this is the dz square orbital. Here, the ligands approach the metal from both ends of x, y, and z axis. The dz square and dx square minus y square orbitals are directed axially and are in line with the ligands. So they get energized and are called Eg orbitals. The dxy, dxz, and dyz orbitals make 45 degrees angle with the axis. So these orbitals get stabilized and are called T2g orbitals. The amount of energy by which the d orbitals are split is called crystal field splitting energy and is denoted by delta O. After splitting, if we watch D4 to D7 configuration, we see that there are two possibilities. If delta O is greater than spin pairing energy P, then T2g orbitals get paired up before filling up of Eg orbitals, resulting in low spin complexes. If delta O is less than spin pairing energy P, then Hund's rule is not broken, and we see unpaired electrons in both T2g and Eg levels, resulting in high spin complexes. One important thing is that the energy of the d orbitals remain the same after splitting. The Eg orbitals gain an energy equal to 0.6 into delta O, while the T2g orbitals lose energy equal to 0.4 into delta O. There is one more thing called the crystal field stabilization energy or CFSE, which is the energy by which a complex decreases due to crystal field splitting. It is listed below. Stability of coordination complexes can be judged by it. Tetrahedral geometry. Here the ligands approach the metal from opposite ends of an imaginary cube. Here the dxy, dxz and dyz orbitals are nearer to the ligands and get energized. The dz square and the dx square minus y square orbitals are directed away from the ligands and get stabilized. Here the crystal field splitting energy is denoted by delta T. Neither of the d orbitals are in line with the ligands, so the splitting is less than octahedral geometry. Tetrahedral complexes are therefore mainly high spin complexes. Square planar geometry. Here the ligands approach the metal from both ends of x and y axis in the xy plane. The dx square minus y square and dxy orbitals which lie on the xy plane get energized. The dz square, dxz and dyz orbitals get stabilized. The crystal field splitting energy delta Sp is very high in this case, and square planar complexes are mainly low spin complexes. The crystal field splitting energy depend on coordination complex geometry, as you have already seen. It also depend on other factors as well. Principal quantum number. Increase of principal quantum number also increase splitting, because as you increase n, the size of d orbital increase, resulting in less ligand-ligand interaction, which effectively will mean more metal-ligand interaction. Oxidation state of the metal. If the charge of the metal ion increase, the ionic radius decrease. This will result in more intense metal-ligand approach, which will result in more d orbital splitting. Strength of ligands. Strong ligand fields cause more crystal field splitting. The ligand strength is arranged in a series called spectrochemical series in order of increasing strength. These ligands on the left-hand side affect very small crystal field splitting energy, and these ligands on the right causes large crystal field splitting energy. This series is called the spectrochemical series because color of coordination complexes is due to dd electronic transition. For a dd transition to occur, it needs energy equal to the crystal field splitting energy. Photon of a particular wavelength which has a specific color has that energy. Take for example the cupric salt solutions which form hexa aqua copper 2 complexes. It absorbs photon from the yellowish part of the spectrum to promote the electron from T2G to Eg level. So aqueous cupric salt solutions are bluish in color, which is complementary to the color absorbed. When you add ammonium hydroxide to the cupric salt solution, there is formation of tetraamine diaqua copper 2 complex. Amine being a stronger ligand, the crystal field splitting energy increases. In that case, it absorbs photon of a bit higher energy. The resulting solution becomes deep blue in color. Limitations of the crystal field theory. It does not account for the covalent character of the metal-ligand bonds. It considers ligands as point charges, which fails to explain why a neutral ligand like carbon monoxide ligand is the strongest. So a new theory called the ligand field theory based on molecular orbital theory was introduced. The ligand field theory was found better than either the valence bond theory or the crystal field theory. Unfortunately, it is also abstract and will not be discussed in this video. But at least I will discuss about the carbon monoxide ligand strength. The molecular orbital diagram of the carbon monoxide ligand is as follows. This is the highest occupied molecular orbital or HOMO which bond with metal. It is a sigma bonding molecular orbital and bonds with the metal like this to form metal carbonyls. This is the lowest unoccupied molecular orbital or LUMO, which is a pi antibonding molecular orbital. Notice that this empty molecular orbital is pi symmetric with the filled d orbital of the metal. Therefore, there is a metal to ligand backbonding possible in this case, which is called pi backbonding. This is an example of synergistic bonding which make the carbon monoxide ligand a very strong ligand.